All right, so good day, one and all. This video is being made to explain some concepts in organic chemistry as taught by Dr. Abner Brody. This material is being made by the GPAC Academic Board, KNUST. Let's keep this caution that this is a supplementary material, not an alternative material. Right, and then this material is being made by students. So should there be any contradiction between that which is said here and that which the lecturer says, there shouldn't be any point of confusion. We go with that which the lecturer says. Very important to note. And then the last thing, which is worthwhile seeing here, is that if you want any clarification with anything here, you see any member of the GPA's academic board for the further clarification. Good. So without much ado, we start. Now, in this particular video, we'll talk about one of the topics, not all, half of the topic. So we'll talk about the dicarboxylic acids. Right, just dicarboxylic acid. Good. Now, we'll focus on the introduction, the nomenclature, and the physical properties. The next video continuation would be focused on the synthesis, the reaction, and then the important dicarboxylic acid. So we are taking these first three, right? And then we are talking about them in this particular video. Good. Now, dicarboxylic acid. As the name implies, di, which means two. Now, carboxylic acid functional group, we know that already, COOH. So usually we are talking about organic compounds that have two carboxyl functional group. Very simple. Good. Now we are seeing that they have the general formula R COOH COOH. So COOH R COOH. Now the R here can be aliphatic or aromatic. Good. Now we are seeing that dicarboxylic acids are suitable substrates. Now, when you are preparing our compounds, our pharmaceuticals, or our compounds in the food industry, we need dicarboxylic acids as suitable substrate for preparation, right? When we are making copolymers, we need dicarboxylic acids such as polyimide and polyesters, right? Good. Now we have dicarboxylic acids that occurs in nature, right? Good. Now example of them, glutamic acid and aspartic acid. So two essential dicarboxylic acids that occur in nature. These are their structures. So you'd see that for glutamic acid, the first dicarboxylic acid, the first carboxylic acid functional group is here. So this is the first carboxyl, second carboxyl, first carboxylic aspartic acid, second one. So these are dicarboxylic acids. Very important. Now, nomenclature. We are saying that the compounds have common names, which are mostly used, right? And then it is worthwhile for you to learn all the common name from n is equal to 0 to n is equal to 8. So we have to know all of them so that if I mention oxalic acid, you should know that it is ethane dioic acid. Very simple. Good. So that is it. Let's take note of all their common names. Next up, the IUPAC nomenclature. So we'll talk about their common names with time, right? Good. So the IUPAC nomenclature, we are saying that aliphatic dicarboxylic acids are named by adding the suffix dioic acid to the name of the parent hydrocarbon. Now, the parent hydrocarbon is determined by using the longest continuous chain that contains the carboxyl group. number the chain from the end closer to the substituent. Good. So these are the rules we have to focus on. We'll have specific examples. Good. So always we get the parent chain. Now we count the parent chain from one carboxylic acid to the last carboxylic acid. So we take them from either side. But always, if they are substituents, we should name it such that we give lowest numbers to the substituents available. So the example, the first one here. Now the name is that we have 3-bromohexane dioic acid. So 3-bromohexane is the parent name. Then we add dioic acid. Right? We could have counted from here. 1, 2, 3, 4, 5, 6. That's hexane, right? Good. In that case, we'd have given 4 to the bromo. If we count from here, 1, 2, 3, and then we can give 3. Now, per the rule, we are saying that we give the smallest numbers to the substituent. So we have to maintain 3-bromohexane dioic acid. Now, the second example, we have 3 carbons, right? So we count 1, 2, 3, 3 carbons, propane. Then we add dioic acid. The next one, we have 1, 2, 3, 4. 4 carbons, butane. Then we add our dioic acid. Good. Now, these are examples for us to try. Good. So without much ado, realize that this 6 here affects the CH2. And so it means we have 6 of this continuing. So we have CH2, 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 COOH. So that's what we have here. So if I'm counting the carbons, it's 1 plus 6 plus 1. That is 8. And 8 is octane. So the name here will be octane dioic acid. Very simple. Now this one I can count 1, 2, 3, 4, 5. 5, pentane. But then there's an unsaturation, so pentene. Now, where does the unsaturation occur? On the second carbon. If you count from here, it's on the second. If you count from here, it's on the third. Usually, you want the smallest number. So 2-pentene. Now we add dioic acid, so we have 2-pentene dioic acid, or pent2-ene dioic acid. Very simple. Now, the next one, we have 1, 2, 3, 4, 5, 6. So 6 is hexene. Because there's double bond, we have hexene, right? Good. Now we have 2 double bonds, so it is hexadiene, right? Now, what is the position of the double bonds? We have it at position 2 and position 4. So we can say it is 2,4 hexadiene dioic acid. If that is too much for us, then we can say it is hexa 2,4-diene dioic acid. So that is what we have here. Very simple, right? Good. The next one, we have 1 plus 7 plus 1, so 9. So nonene dioic acid. Very simple. Now we are still talking about nomenclature, but now we are talking about cyclic dicarboxylic acids. So we are saying for them, the parent hydrocarbon ring is named. Now after naming, we number the position of the carboxyl groups on the ring, and then we add the suffix dicarboxylic acid. And so we realize that this parent chain here is hexane, right? Now the dicarboxylic group falls on position 1 and 2. So we see it is cyclohexane 1,2 dicarboxylic acid. Now this is a benzene ring. The substitution is on position 1 and 3. So we have benzene 1,3 dicarboxylic acid. Now, common name again, systematic name. So this is a very common compound that we would encounter in so many areas as we go along this discussion, which is worthwhile taking note of. Very important. Good. Now, the first one, it's the same compound anyway, it's just isomers, structural isomers, right? So we have benzene with 2 dicarboxylic acid, that's 2 carboxyl functional groups on it. right? This is position 1, 2, position 1, 3, position 1, 4, right? And so we are seeing that this is autotalic acid, auto position. Butalic acid is called the normal talic acid. So once I mentioned talic acid without saying anything, it means you're talking about autotalic acid, right? Then we have isotalic acid, that's the meta. And then we have terephthalic acid, that is the para. Very simple, terephthalic acid, para. Now we are supposed to do this exercise, a very simple one. Good, so let's see how we go about that one. So the first one, we are asked to draw cyclobutene 1,2-dicarboxylic acid. So cyclobutene is like this, right? 1, 2, so 1, 2 dicarboxylic acid, so COOH, COOH, right? It has this 1, 2 dicarboxylic acid. Next one, we are supposed to draw decaying diaric acid. So I can write HOOC, then C2, so 8COO. Now I'm writing 8 here because these carbons will be added to get my 10 decaying, right? Then I have acetylene dicarboxylic acid. Styrene is carbon, triple bond carbon, right? So acetylene dicarboxylic acid, COOH, COOH, right? Good. Then the last one is cyclopentane dicarboxylic acid. So this is my cyclopentane, cyclopentane 1, 3. So position 1, then position 3, COOH, COOH. Very simple, right? Good, good. So that is it. That is all. Very simple, very simple. Good. Now, physical properties of dicarboxylic acid. We are saying that dicarboxylic acids are colorless, odorless, crystalline substance at room temperature. Good. Now, what is very important to me here, because I will need it in one of the explanations, is that it is a crystalline substance. Now, from basic physics, we know the behavior of a crystal, that in every crystal, the molecules are arranged, or the atoms are arranged in a particular order, right? And then the order is that's the occupy crystal lattice. So they are fixed positions in the compound that they occupy, crystal lattice. Good. So let's keep that in mind. We'll use that in explanation as we go along. So this is a table of the common name against their systematic name. Now we have to know all the names here. We should know all of them, right? The common name from. So there are simple ways of getting these names. Other people want to learn like that. One of the common way is so I think it was, oh my son, go and play Subway at Sabia. So let me write it here. Good. So a very simple one. Oh my son, go and play Subway at Sabia. So the O is 2 carbons, that is ethanoic acid, oxalic acid. Mine is malonic acid. The sun is succinic acid. Go is glutaric acid. A is, the end is adipic acid. P is pimelic acid. Subway, that's subbaric acid. That is azelaic acid. And then the sabia is sebacic acid. So very simple. You can just use this to get the first letters for each of the instants. Very important. Now, after that, we have their formula there. The next property we see is the molecular weight. We realize that as you go down, now what happens to the molecular structure? We are adding a methylene group, which is roughly around 14 units, right? And so as we go down, we are expecting the molar mass to increase roughly by 14, right? The molecular weight of the compound, that is what we see here. That is what we see here. Very simple. Now, the melting point here will alternate between even and odd numbered carbon atoms. So you realize that the even ones are high, the odd ones are low. That is, if you compare the even one next the subsequent odd ones. That is the order until you go down there, where the order changes because of other reasons. Now, you realize that the even numbered, that's the dicarboxylic acid with the even numbered carbon atoms, they have higher melting point because, first of all, they are solids, right? Now we are saying they are crystalline solids. Crystalline solid will have to arrange themselves in crystal lattices, right? Now the even numbered ones can arrange themselves properly. So proper arrangement, that is the key word. Now, because of proper arrangement in this crystal lattice, what will happen is that their extent of bonding will be enhanced. Now, once their extent of bonding is enhanced, you require higher energy to break them apart. So that is for even. Now, the odd numbered ones have poor arrangement. So the atoms are odd numbered, poor arrangement. Now, once they have poor arrangement, the extent of bonding is reduced. Now, once the extent of bonding is reduced, it is easier for you to break them apart. So that is the reason for the melting point, right? Now, there are other properties being explained here. We talked about they have shown us the boiling point, they have shown us the density, they have shown us solubility. It is worth noting that what happens at the melting point, the opposite happens at the solubility. That is, the odd numbered ones are more soluble. They are more soluble because in between the molecules, the bond there is weak because of improper arrangement. So it is easier for them to interact with water. That is the solubility we are talking about, the environment, than the even numbered ones, which are well bound to each other. So the even numbered ones are well bound to each other. It is difficult for you to interact with water or the external environment. But then the odd numbered ones, they have loose bonding between themselves, so they can easily interact with the environment or water to dissolve. That is the solubility we are talking about. When we talk about density, what happens here is that density depends on mass and volume, right? Good. Now, as you go down, right, as you go down, the mass increases, of course, but then there's also increase in volume. Now, the increase in volume here supersedes or overcome the increase in what? In mass. So what happens is that the overall density will decrease. So the molecule becomes lengthier, it becomes bulkier as you go down, right? And that's marvelous or significant increase in the volume would overcome the change in mass, that's the increase in mass, and make the net density decrease. That is what we have here. Good. So a lot of things to learn from the table. Good. Now, far from here, we have to, so just around the table, we discuss melting point. An even number of carbon atoms have higher melting point than odd numbered dicarboxylic acid and decreases with chain length, right? Good. Now we are saying that solubility, dicarboxylic acids with even numbered carbon atoms are less soluble in water than the next higher homologous with odd numbered carbon atoms. Now, as the chain length increases, the influence of the hydrophilic carboxyl group diminishes. That's N is equal to 5, pimelic acid onwards. Solubility in water decreases rapidly. So they are saying that as the chain length increases, the influence of the hydrophilic carboxyl group decreases, right? Good. So you realize that the solubility was alternating between odd and even, but from pimelic acid onwards, the solubility was decreasing. So at that point, we didn't care about whether you are odd numbered or even numbered. It was decreasing from pimelic acid because the compound was becoming non-polar because the hydrocarbons were increasing. That compound was becoming non-polar. And so now it was decreasing generally. That's the whole discussion in regards to this one, right? And we are saying that most dicarboxylic acids dissolve easily in lower alcohols. Very important. Lower alcohols. We are saying most of, not all of them, because when the length increases, what happens that they become more non-polar. But the normal dicarboxylic acid we know are polar, right? Now, if they are polar, they are dissolving in alcohols. Not every alcohol, but lower alcohol. Talk about lower alcohol, we are talking about alcohols with few carbons. Something like methanol, ethanol, right, can dissolve dicarboxylic acid at room temperature. Now, lower dicarboxylic acid are practically insoluble in benzene and other aromatic compounds. This is an important statement to also note. Benzene and then aromatic solvents are known to be non-polar. Lower dicarboxylic acids, if we say they are lower, it means they have few carbons. So we are talking about oxalic acid, those ones. Now, because the carbons are very low, they have high polarity. And because they have high polarity, it is practically insoluble in benzene, because benzene is also highly non-polar, right? Very simple. Now we are seeing the density decreases steadily with increasing length, and that has also been explained. Good. Now this is a different table. Yes, trying to show us different properties. So this is more of the acidic nature. Now, the parameter mentioned here is pKa. So it is worth explaining the implication of pKa here. Now, when we were doing our inorganic, what we came across was Ka. And then we said the Ka for a weak acid. We measure Ka for weak acids, right? And the Ka is directly proportional to the strength of the weak acid. It shows the extent of dissociation, right? So if you have a higher Ka, let me write that down. If you have a higher Ka, then your acidity is high, right? Good. Now, we are talking about pKa. pKa is a negative log of Ka, and then the scenario changes. So if you have a lower pKa, you have a higher acidity. So a higher Ka will correspond to a lower pKa, and both will correspond to a higher acidity. Very simple. Let's look at the table. So you realize that each of the compounds or each of the dicarboxylic acids here have two pKas, right? Yes, and then we have pKa1 and pKa2. First thing to note here is that they have the ability to donate two protons. Now, the two protons don't go at a go, they go in succession. So it goes first, it can donate the first proton, that will be the pKa1, and then it will donate the second proton, that will be the pKa2, right? Good. Now, the next thing we have to note here is that always the pKa1 is smaller than the pKa2. So we say that in the first instance, when you are losing pKa, that's the first, when you're losing the first proton in pKa1, you are losing it from a neutral atom. And that compound's acidity, look at the whole compound here. Now, the carboxyl group is known to be an electron withdrawing group. So what happens here is that this functional group is acting as electron withdrawing group for this functional group, right? And so enhance the acidity of this OH bond, the polarity and the acidity of this OH bond, right? So it is easy for you to lose the H plus, right, in the first instance. Now, after losing the H plus, the anion formed is stabilized by hydrogen bond. Now, because the anion formed is stabilized by a hydrogen bond, which is specifically intramolecular. Now, note this, that the hydrogen bond we are talking about, assuming I lose this hydrogen, H plus, the anion formed here is stabilized by intramolecular hydrogen bonding. Very important. So the interaction we are talking about here is this hydrogen interacting in a way with this hydrogen. Even though it can interact with other things in the medium, this is what we are talking about when we are talking about this explanation, right? Because of this stabilization, it is difficult for you to lose the second hydrogen, because the second hydrogen here has been involved in what? Hydrogen bonding. So that's what we are talking about. So it is always easier for you to lose from the neutral one than you losing from a singly charged anion as a dicarboxylic acid. That is why you realize that the acidity here, the number is small, meaning it's high acidity, but acidity is lower in the pKa. So that's when it's losing the second one. Now, we are also notice that the difference between pKa1 and pKa2 will decrease as you go down. And then the difference is coming in because of the strength of the hydrogen bond formed after you have lost your first proton. So after the first proton has been lost, there's hydrogen bond formed, right? But then if we have a higher difference like this one, the difference approximately 3 here. Now the difference here is approximately 1 point something. So we realize that as you go down, the difference will reduce. That is because the strength of hydrogen bond formed after the loss of the first one is reduced, right? Good. So the difference here reduces because the hydrogen bond, so the difference is just due to the hydrogen bond formed. Now, as you go down, the difference reduces because the hydrogen bond, the strength of the hydrogen bond formed will also reduce. Very simple. Very simple. Good. Next up. So we are talking about acid strength. Though two carboxyl groups of a dicarboxylic acid are identical, the two pKa values are different because protons are lost one at a time and therefore leave from different species. The first proton is lost from a neutral molecule. The second proton is lost from a negatively charged ion. So that is what has been shown here. Neutral molecule losing, that is pKa1, and then the singly charged anion losing another proton becomes the pKa2. But now we are seeing that after removal of a proton, the anion is stabilized by hydrogen bonding as a result of loss of second proton becomes difficult. Now we are seeing that the less the number of carbons separating the two groups, the stronger the hydrogen bonding, right? So if you have, let's say, one carbon separating the two carboxyl groups, the hydrogen bonding, that's the intramolecular, this is what makes it clear that if the chain length becomes longer, that's if the carbon separating the two carboxyl group becomes longer or becomes a lot, what happens that the two carboxyl will be far apart, so the bonding is not really enhanced, right? But then if they are closer, that if we have less carbon, right, then the bonding becomes very strong, and in that case will result in a higher difference between pKa1 and pKa2. Now we are seeing dicarboxylic acids have two separate ionization constants. The first ionization constant of dicarboxylic acid is larger than the Ka for monocarboxylic. So now we are comparing dicarboxylic acid to monocarboxylic acid. Now, the reason why the pKa1 for dicarboxylic acid is larger, the pKa will be smaller, right? But the Ka will be larger. Now, in this case, they are talking about the Ka. So they are saying it's larger than the Ka for monocarboxylic acid. Is that now the dicarboxylic acid we have two carboxyl groups. And as I mentioned, one of the carboxyl group will act as electron withdrawing group for the other one. So it will withdraw electron and enhance the acidity. While the monocarboxylic acid, they have just one carboxyl group to act as acid. Dicarboxylic would have two, and once is enhancing the ability of the other one. So one of them is enhancing the ability of the other one. And so it's always easier for you to lose from one of that's in the pKa1, right? So they are saying one carboxyl group as electron withdrawing group to facilitate the dissociation of the other one. This is particularly noticeable when the two carboxyl groups are separated by only a few bonds, as in oxalic acid and malonic acid, for example. Good. Are several magnitudes stronger than the alkyl derivatives of acetic acid. Now, when the chain length increases, so we are seeing that heptane dioic acid, in which the carboxyl groups are well separated from each other, is only slightly stronger, right? So it means that carboxyl group enhancing the acidity of the other carboxyl group is reduced if the chain length increases. Very simple. Good. Now we are seeing dicarboxylic acid have two separate Ka. We have talked about that already. Yes, so we've talked about everything here. Good. An exercise for us to try. Now they are asking us why first Ke of malonic acid is much lower than that of acetic acid. Now, when the pK is lower, it means the acidity is high. So they're asking us why malonic acid is more acidic than acetic acid, right? That's the first question. Now, the second one is asking us, whereas the second of malonic acid is much higher. So we'll talk about the first comparison as in malonic acid has two carboxyl group, where one is enhancing the acidity of the other. Acetic acid just has one, right? Now, if it comes in the second instance where it becomes a weaker base in terms of the pKa2, then we argue out that after the first proton has been lost, the anion is stabilized by hydrogen bonding. So losing that hydrogen that is involved in hydrogen bonding is quite difficult, right? So we reduce the acidity, something very simple. Good. Now, the next exercise, we are seeing the difference in pKa values for dissociation of first and second protons of adipic acid is about 1. And then that of oxalic acid is about 3 units explained. Good. Now, the simple explanation or the straightforward explanation for this one is that the difference is just related to the strength of the hydrogen bond then formed. And so the oxalic acid, the hydrogen bond form is stronger than the adipic acid. And so you realize that between pKa and pKa2, because there's a strong hydrogen bond, there's a bigger difference, right? But then here we are expected to present the difference from as has been presented. So you have to talk about pKa1, talk about pKa2 before we come to the main thing. So that is what has been presented here. So you have to start by saying that carboxylic acids have 2 ionization, and pKa1 is always smaller than pKa2. And we'll talk about the fact that the first one is removed from neutral, second one is removed from negatively charged, right? Good. Before we come to our main case, which is this one, that's in case of oxalic acid, the carboxylate group and the carboxylic acid are close enough, intramolecular. They are close. So the carboxylate group is the one that has lost the proton, and the carboxylic acid functional group is the one that still has the proton. Now they are very close to form hydrogen bond. And then because the hydrogen bond is formed, you require more energy to remove the proton, right? Good. And then in the case of adipic acid, they are not really close. So after losing the first one, the carboxylate group and the carboxylic acid functional group, right? They are not exactly close to form a very strong intramolecular hydrogen bonding. Good. And therefore, the energy will be less. So the difference is less. Very simple. Very simple. Good. Now, the next thing here is a question. They are comparing malic acid and then fumaric acid. Now, these are equal. I mean, it's just cis and trans different. So malic acid is cis, fumaric acid is trans, right? Good. Now we can compare their pKa1 and pKa2. So realize that pKa1 for malic acid, right? For malic acid is smaller than the fumaric acid. Now this shows that malic acid is more acidic than fumaric acid, right? Good. Now the explanation is because of the proximity of their of their carboxyl groups. So realize that malic acid, because of the cis configuration, the carboxyl group here is close to this one. Now because they are closer, this one enhancing the acidity of this one is more efficient than this one, because in the trans configuration they are far apart, or they are further apart, right? So the ability to enhance, the ability of one carboxyl group to enhance the acidity of the other carboxyl group is reduced. So that is what we talk about here, right? Good. Now the pKa2, you realize that malic acid has jumped, right? And then fumaric acid is still within range because after the loss of the first proton, right, the anion is stabilized by intramolecular hydrogen bonding, right? And so if assuming we lost the proton from here, if we lose the proton from here, this is the negatively charged PC. Now there's an oxygen with there's another hydrogen here, right? Now the distance here is quite close. So between this anion and this hydrogen is close. But look at this. If we lose this proton here, this is a very far distance. So you realize that the hydrogen bond formed by the cis, that is the malic acid, is stronger. So you require more energy to remove this hydrogen than in the case of this, because this is very weak. So you can just remove the second one with relatively less stress. Very simple, or relatively less energy, right? Very simple. So that is what we talk about. So they're asking why K1 for malic acid is greater than fumaric acid. Now, K1, yes, of malic will be greater because the pKa is smaller. Very simple. K2. So K2 for malic acid is bigger here because we are talking about pKa. But then if it were to be the K, it would have been smaller. So that is just the different playing around words, I would say. Now, assignment for us to solve. We have to explain the statement. Is pKa1 for dicarboxylic acid greater or smaller than pKa for monocarboxylic acid? So explain. They are asking us if that is the case. We have talked about this already, that pKa1 for dicarboxylic acids are smaller because they are more acidic than monocarboxylic acid, right? And we talked about the fact that one carboxyl group enhances the acidity of the other carboxyl group. Right? Now, the difference between pKa1 and pKa2 for dicarboxylic acids of this type decreases as chain length increases. That is true. The difference would yes. Okay, it's even a true statement. So we are supposed to explain, so I don't have to say it's true. Yes, but then it is true because as the chain length increases, that's as the N increases, the interaction, that is the proximity or the closeness of the carboxylate group after the loss of the first proton and the carboxylic acid functional group, right, increases. So they are no more proximal, or they are not close enough to form the intramolecular hydrogen bond, right? They are not close enough. You realize as the chain length increases, the hydrogen bond formed between them will decrease, and then the difference between pKa1 and pKa2 would also decrease. Very simple. The last question, we are supposed to arrange oxalic acid, malonic acid, succinic acid, glutaric acid in order of acidity. That's first ionization, right? So if we are arranging, it depends on the order that we are talking about here, right? If we want to do it from the biggest to the small, that's the most acidic to the least acidic, it will be the same order as oxalic, malic, succinic, and glutaric. But if we want to arrange it from the least acidic to the most acidic, then we change it from glutaric, succinic, malic, and then oxalic. Very simple, right? Good. And then we are counting for it's just the acid enhancing ability of one carboxyl group against the other, and then the increase in chain length, right? Because always in the pKa1, one carboxyl group should enhance the acidity of the other carboxyl group, but the effect of one carboxyl group on the other one will decrease as the chain length increases. And so if you talk about oxalic acid where there are no carbon between the two carboxyl groups, one carboxyl group enhancing the acidity of the other one is high. That is the highest. If you talk about glutaric acid where we have like 3 carbons between the carboxyl groups, right? One carboxyl group enhancing the other carboxyl group's acidity is what is reduced. Very simple. Now, there's something for us to note here, that acid in which there are 2 carboxyl are separated by chain of more than 5 normally behave more or less independent of each other. That is, if the chain length is more than 5, that's greater than 5. So if N is equal to 6, right, that's if you are going to the nonane dioic acid, those ones, for those ones, the effect of one carboxyl group on the other one is quite negligible. So the 2 carboxyl groups are approximately behaving as independent entities. That's what we are talking about here. Good. So we'll end this video here. It's introductory part, trying to explain the concept, the property, and all. We'll do another one to explain the synthesis and the reactions and the importance of dicarboxylic acid. Thank you very much. And if you have any question, kindly see any member of the GPAC Academic Board. for further clarification.